In this video, we look at the work on power series for Module 4 of the WJEC Further Mathematics Specification. And what we need to be able to do is use Maclaurin series, in particular the Maclaurin series for e to the x, ln, the natural logarithm of 1 plus x, sin x, cos x, and 1 plus x to the n. And we need to be aware of the range of values of x for which they are valid. So the key result is what actually is the Maclaurin series. So the Maclaurin series for f of x is f of 0 plus x times the first derivative of f at 0 plus x squared over 2 factorial times the second derivative of f at 0, and so on. The series may be valid for all values of x, or it may just be valid for a small interval of values of x. The commonly occurring Maclaurin series are all given in the formula booklet, so make sure you know where to find those. So you can move straight away onto looking at some examples on Maclaurin series. So the first one, we have the function f is defined by f of x is the natural logarithm of 2e to the x. Take away 1. We have to first of all show a result about the second derivative of f, and then we have to deduce the Maclaurin series for f of x as far as the term in x cubed. So we've got f of x is the natural logarithm of 2e to the x. Take away 1. So if we've got to find f double dash x, we need to differentiate twice. So the chain rule will be used to find f dash x. The derivative of 2e to the x, take away 1, is just 2e to the x. The derivative of logarithm of something is 1 over the logarithm of something. So using the chain rule, we've got the derivative of natural logarithm of 2e to the x, take away 1, is 2e to the x times by 1 over 2e to the x, take away 1. In other words, 2e to the x over 2e to the x minus 1. We want to find the second derivative of f, so we need to differentiate again, and this is going to require the quotient rule. So we've got to first of all differentiate 2e to the x, this is finding u dash, and multiply it by v. So we've got the derivative of 2e to the x is 2e to the x times by v is going to just give me 2e to the x times by 2e to the x, take away 1. We now need to subtract u times v dash. U is 2e to the x, and the derivative of v is 2e to the x as well. So the top of our fraction is going to be completed by minus 2e to the x times 2e to the x divided by v squared, so that's divided by 2e to the x, take away 1, all squared. We need to tidy up the numerator of this fraction. So if we multiply the brackets out from the top, we get 4e to the 2x, take away 2e to the x, minus then 2e to the x times 2e to the x, which is 4e to the 2x. So what we're left with on the numerator is just the minus 2e to the x. No need to do anything at all with the denominator, and we have established the required result for the second derivative of f. So we now need to find the Maclaurin series for f of x as far as the term in x cubed. Well, we know that the Maclaurin series is given by f of 0 plus x times the first derivative at 0 plus 1 over 2 factorial times x squared times the second derivative at 0 plus 1 over 3 factorial x cubed times by the third derivative at 0. From the definition of the function, we can see that the value of f of 0 is just the natural logarithm of 1, which is 0. We've already established the result that the derivative of f is 2e to the x divided by 2e to the x take away 1. So the value of the derivative of f at 0 is 2 divided by 1, which is just 2. We've established the result for the second derivative of f. So the value of the second derivative of f when x is 0 is minus 2 divided by 1 squared, and that just gives me minus 2. So from what we've already done, we can say that the Maclaurin series for f of x is 0 plus 2x minus x squared plus 1 over 3 factorial x cubed times the third derivative of f at 0. So we've got one more differentiation to do. So we know that the second derivative of f is minus 2e to the x divided by 2e to the x take away 1 squared. So we're going to have to use the quotient rule again. So we've got u is minus 2e to the x and v is 2e to the x take away 1 squared. So the first component of our quotient rule is going to be u dash times v. The derivative of minus 2e to the x is itself minus 2e to the x times by v, which is 2e to the x take away 1 squared. Now the second part of the numerator is u times v dash. We know what u is, so we've got to subtract minus 2e to the x times by the derivative of v. So we need to differentiate 2e to the x take away 1 squared, which requires the chain rule. And using the chain rule, we obtain 2e to the x times by 2 lots of 2e to the x take away 1. So the v dash term on our quotient rule is 2e to the x times by 2 lots of 2e to the x take away 1. And then we have to divide all of that by v squared, which is 2 lots of e to the x take away 1 squared, itself squared. Now all we want is the value of the third derivative when x equals 0. So the sensible thing at this stage is not to do any simplification of that horrible fraction. It is simply to substitute x equals 0 into that expression. And if we substitute x equals 0 in, the numerator becomes minus 2 times 1 squared, which is just minus 2. And then we have got negative 2, so that's plus 2 times 1 times 2 times 1 times 2 times by the bracket, but 2e to the 0 take away 1 is just 1 again. So the whole of that second term in the numerator is just worth 8. The denominator, well, we already know 2e to the 0 take away 1 is 1. Square it, still gives me 1. Square it again, gives me 1. So I'm just ending up with 1 to the power 4, in other words 1. So the value of f, the third derivative of f at 0 is 6. So the Maclaurin series, which we already know starts off as 2x minus x squared, the x cubed term is going to be 1 over 3 factorial times x cubed times by 6. Well, 3 factorial is 6, so that's 1 over 6 times x cubed times by 6. In other words, it's just x cubed. Moving on to a second example, and this example requires the work on hyperbolic functions. We've got the function f of x this time is the natural logarithm of 1 plus sin x. We've got to find the first 3 non-zero terms of the Maclaurin series, and then we've got to use that to make some deductions about the function f. So, f of x is the natural logarithm of 1 plus sin x, and we know that the Maclaurin series for a function is f of naught plus f dash naught times x plus the second derivative evaluated at naught divided by 2 factorial times x squared plus the third derivative of f at naught divided by 3 factorial times x cubed, etc. So, f of naught is the natural logarithm of 1 plus sin naught. Sin of naught is naught, so it's a natural, f of naught is just the natural logarithm of 1, which is 0. So we've got f of naught is naught. To find f dash naught, we're going to have to differentiate, which is a chain rule. The derivative of 1 plus sin x is cos x. The derivative of ln of something is 1 over the something. So the chain rule is just ending up telling me that the derivative of natural logarithm of 1 plus sin x is cos x over 1 plus sin x. Substituting x equals naught in, we've got f dash naught is cos of naught, which is 1, divided by 1 plus sin of naught. Sin of naught is naught, so we've got a fraction which is simply 1 divided by 1 plus naught, which is 1. We now need to differentiate to find the second derivative of f, and this can be done using the quotient rule in a very similar way to the previous example. So the details are all there. Again, for you to check through. And we can then at that stage substitute in x equals naught and calculate that the second derivative of f at x equals naught takes the value minus 1. Now we're asked in the question for the first 3 non-zero terms of the Maclaurin series for f of x. So what we've got for the moment for the Maclaurin series is naught plus 1 times x plus minus 1 over 2 factorial times x squared. So what we've got at the moment is x minus a half x squared. We've only got 2 non-zero terms. We're going to have to go ahead and work out, find the next non-zero term in the Maclaurin series. So we're going to need the third term in the Maclaurin series, certainly. It requires us to do another differentiation. So we know that the second derivative of f is sin x take away 1 over 1 plus sin x squared. So using the quotient rule with u equals sin x minus 1 and v equals 1 plus sin x squared, then our u dash is cos x times by v is 1 plus sine x squared. Take away u, that's sine x take away 1, times by the derivative of v. Now to differentiate 1 plus sine x squared, we need to use the chain rule. The derivative of 1 plus sine x is simply cos x. The derivative of something squared is 2 times the something. So the derivative of 1 plus sine x squared is cos x times by 2 lots of 1 plus sine x. So that's the numerator of my third derivative. The denominator is going to be v squared, so that is 1 plus sine x squared squared. In other words, 1 plus sine x to the power 4. We need the value of the third derivative when x equals 0. Again, we're not going to do any simplification of the expression for the third derivative. We'll simply substitute in x equals 0. So the third derivative when x equals 0, we've got cos of 0 is 1 times by 1 plus sine 0, that's itself 1 squared. So the first term is simply 1. Take away sine x, take away 1. Sine of nothing is nothing, so that's 0 minus 1 is minus 1. So I've got minus 1 times by cos 0, 1 times by 2 lots of 1 plus sine 0, which is 2 lots of 1, which is just 2. Tidy all of that up, I see that the third derivative of f at 0 is 3. So I know now that the Maclaurin series for f of x is 0 plus 1 times x minus 1 over 2 factorial times x squared plus 3 over 3 factorial x cubed. In other words, x minus a half x squared plus a third x cubed, plus a half x cubed. 3 over 3 factorial is 3 over 6, which is a half x cubed, plus the higher terms. We've got a mixture of odd and even powers in the Maclaurin series for f of x. And that certainly means that f cannot be even, because if it was an even function, all of the powers in the Maclaurin series would be even powers, and it can't be an odd function, because if it's an odd function, then the Maclaurin series will consist simply of odd powers. So the function is neither odd nor even. Finally, we're asked to use, given the fact that ln of 1 plus sine x equals 10x squared has got a small positive root, it wants us to use the Maclaurin series to find its approximate value, corrected to significant figures. Well, we know that the Maclaurin series for ln natural logarithm of 1 plus sine x is x minus a half x squared plus a half x cubed. So what we're looking for is we want x minus a half x squared plus a half x cubed to be very, very close to 10x squared. In other words, we're looking for x minus 10.5x squared plus 0.5x cubed to be 0, or very, very close to 0. If we factorise that, we've got x times by 1 minus 10.5x plus 0.5x squared. We want to be very, very close to 0. Now, obviously, x equals 0 is a possible solution, or we've got 1 minus 10.5x plus 0.5x squared equals 0. we're looking for the small positive root. If we solve the quadratic equation, 1 minus 10.5x plus 0.5x squared equals 0, gives me x is 20.904 or 0.0957. So the small positive root that we're looking for is x equals 0.096 to two significant figures.